All right, everybody. I think I'm going to go ahead and get started. It is 1 o'clock and it's hot Thursday afternoon out there. I hope that you guys have working air conditioning in your cars and homes, wherever you're headed later today. It's going to be hot for a couple of days. I'm going to have to wait on my basketball sessions for a little while, I think, outdoors. But that's okay. Let's see. Today, we are going to finish chapter 5, actually. And I will give you a quick overview about our upcoming midterm just a little bit later in our class. But I'd like to start with just picking up where we left off in the material on Tuesday. And as I said, we're going to finish chapter 5. I think this lecture should be pretty chill, pretty decent. It's very computational for the most part. I don't think it's going to be anything too crazy. If you remember, we're talking about these geometry ideas in a vector space. And in order for us to be able to do that, in order for us to be able to talk about geometry in a vector space, we have to introduce an inner product. It's kind of like a dot product. It's essentially what we're doing. So it's the inner product gadget, which is denoted with these angled brackets, that allows us to introduce things like norms and angles. And the most recent concept from geometry here, guys, is orthogonal, right? Two vectors are orthogonal if their inner product is equal to 0. And the inner product has to be coming from some formula. So taking the vectors v and w, you plug them into the formula for this gadget and just see if you get 0. Okay? What that formula is usually has to be given to you unless it's like a standard dot product. Sometimes it's just a regular dot product. Now, I also mentioned the idea of having an entire set of orthogonal vectors. So a set S is an orthogonal set if for every pair of vectors in the set, the inner product comes out to 0. So you have to check every single pairing, right? V1 with V2, V1 with V3, V1 with V4, V2 with V3, blah, 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 however many vectors there are. You have to check all of those pairs, but as long as they are always 0, then you have an orthogonal set. And in addition, if all of the vectors are unit vectors, then it's called an orthonormal set, right? So in that case, you have what's called an orthonormal set. Okay? So far, so good? These are just the definitions from last time. I thought maybe we would warm up today with an example. Not that we need to get warmed up on a day like this, but I thought we'd take an example to just kind of practice. Does that sound good? So take a look with me here. The warm-up problem here is I would like to show that this set, which has a 1 and a square root of 3 times the quantity 2x minus 1, I would like to show that that is an orthonormal basis for P1 of R. So the universe that I'm working in is polynomials. These are polynomials of degree 1 or less. And I would like to show that these two polynomials here form an orthonormal basis. By the way, when I say orthonormal basis, what I mean is they are a basis and they are orthonormal as a set. Okay. So to show that this is an orthonormal basis, I have several things to do. I have to explain why it's a basis in the first place. And then in addition to that, well, why is it actually orthogonal and orthonormal? Everybody got the big picture here? Does anybody see anything wrong with the question as it's stated there on the board? Are we going to be able to do this problem? Gabriel, you're shaking your head no. Why not? I've done a flaw on purpose to see if anybody notices what's missing here. Levi?
Oh, wait, is the P1 of R? You didn't give us a formula.
I didn't give you, so it's P1 of R, and I did not give you what? Well, these are the two polynomials that we're going to work with, right? But I did not give you an inner product formula. Did you notice that? I did not give you an inner product formula. So how are you going to know if your vectors are orthogonal or orthonormal? All of these definitions involve using the inner product. There has to be an inner product. So if you saw something like this, you would go to whoever was asking this question and say, you know, this doesn't work. This doesn't make any sense. So what I'm going to do is fix that. I'm going to fix that by saying use the inner product. Use the inner product. So I'm going to just make an inner product here, guys, between two vectors f and g. These are both going to be polynomials. And I'm going to use the one that was in my video that you watched, which is where you just do an integral from 0 to 1 of f of x times g of x times dx. So I'm just going to use that one. This one was in the video. It's like a very important example of an inner product. Okay? Everybody with me so far? That second line has to be there, guys. Otherwise, the question does not make sense. It does not make sense to ask you questions about angles or magnitudes or lengths or perpendicular or orthogonal vectors. None of that makes sense unless you have an inner product that you know that you're working with that. You have to be working with an inner product. So here now I gave it to you. So let's get into it. Now we can get into actually doing the problem. The first thing I would like to figure out, guys, is why are these two vectors a basis? Let's not worry yet about the orthogonal or orthonormal part of it. Just why are they even a basis at all? So I'll get my solution started here. Does anybody think they have any insights for me? Like, why could I look at these two polynomials and imagine that they might be a basis for P1 of R? This is actually goes back to chapter 4. It's a nice chance to review.
They have the right dimension.
They have the right number of vectors. Do you remember how we did that? We would, so let's just recall. I like that, Ryan. So what is the dimension of P1 of R? Anybody remember? 2, right? Got to know that cold. So the dimension of P1 of R is 2. And how many vectors were we given in our set S? 2, right? So that was what I called K, right? So K is equal to 2 as well. So the dimension of the space matches how many vectors I gave you. What that means is that this set is either both or neither. Remember how we were doing that whole analysis? Okay, so if it's the right number of vectors, then they are either both Li and a spanning set, or they are neither Li nor a spanning set. That's the possibilities that we have here. We went over that in detail on Tuesday. So can somebody tell me why it's both? Like, can you tell me why are these vectors Li or why are they a spanning set? Why are we getting a thumbs up on these issues? Gabriel? Okay, we could put them into a matrix if we wanted to and take some kind of a determinant, but there's an easier way here. It's an easier way to do it. Josh? Exactly. These are only 2 vectors and they are not scalar multiples of each other, right, guys? You cannot take this guy right here, 1, and multiply it by a number and get this one. They're not scalar multiples. So I'm just going to say, since the given vectors in S are not scalar multiples, and there's only 2 of them, they are not scalar multiples, then therefore they are Li. They are Li. So that is one way. When I have only 2 vectors, as long as they're not scalar multiples of each other, we can say that they are Li. Right. And if it is thumbs up on Li, then it's also thumbs up on spanning V. Because remember, it's both or neither. Right? Okay, so therefore, thus S is a basis for P1 of R. In other words, it's both linearly independent and a spanning set. I like this problem, actually. It's a nice review of chapter 4, and now we're going to build off of that a little bit more. Okay, so we have a basis, but the question is asking us to show that we have an orthonormal basis. So you have to remember what orthonormal is. Orthonormal just means it's orthogonal and the vectors are unit vectors. Let's check that it's orthogonal. Let's check that it's orthogonal. I'm going to do that right here with you guys. Orthogonal. Let's see if we can understand why are these vectors orthogonal. Well, orthogonal just means the inner product of the two vectors should be 0. So let's check it. Let's take the inner product of 1 together with the square root of 3 times the quantity of 2x minus 1. Let's take that inner product of those two functions. And see, this is where we have to have this formula. This has to be part of the given question here, right? So this is going to be an integral from 0 to 1 of f of x times g of x times dx. Well, that's just the product of these two things. Square root of 3 times 2x minus 1 dx. And if you pull out the radical 3 and then you integrate 2x minus 1, the antiderivative of that is just x squared minus x. I have to evaluate that from 0 to 1. And when you plug in the limits of the integration here, guys, it absolutely does give you 0. We were supposed to get 0 if they're orthogonal, right? So we get 0 out of that. Okay, so the vectors are orthogonal. So that means we not only have a basis, we have an orthogonal basis. You with me? Now they're asking for even more than that. It says here orthonormal basis. So I have to check what's the orthonormal part. In addition, the norm of every vector has to be 1. Let me just remind you the norm. So this is an important one, guys. The norm of a vector is just the square root of the inner product of a vector with itself. So this one, we use that one a lot in this chapter, the norm of a vector. So let's check it. Let's check the orthonormal part now. Okay, so I have to check the norm of 1. And then after I do that, I'm going to come down here and I'm going to check the norm of radical 3 times 2x minus 1. I've got to work both of these out and see what I get. I should get 1, right? The answer we're looking for is a 1. And I just want to work it out. So for this first one, just using my norm formula, it's the square root of the inner product of 1 with itself. And so underneath this radical, I have to do an integral now. The inner product of 1 with 1, I'm going to integrate from 0 to 1 of 1 times 1 with a dx on that. Just using this formula right here. Okay. Now the integral of dx is just x, and I'm going to evaluate that from 0 up to 1. And of course, this is a simple calculation. You just end up getting a 1 out of that. Okay, so that is a unit vector, right? If the norm of a vector is 1, we call it a unit vector. So far, so good? The second one's a little bit messier, but we should end up also getting a 1 as the answer. Let's check it. If I take the square root of the inner product of radical 3 times 2x minus 1 with radical 3 times 2x minus 1. Okay, so it is a little messier, but it's the same concept. Underneath this radical, we are going to have an integral that we have to look at. It'll be an integral from 0 to 1. And what I have to do for the integrand is multiply the two functions together. Radical 3 with a radical 3 makes a 3. And then I have two factors of 2x minus 1. So that's 2x minus 1 squared as well. Yeah. Let's go with something like that. And you can do this with a u substitution if you want. So you could let u equal, I don't want to dwell on this too much, but you could let u equal 2x minus 1. If you did that, then the du would be 2 times dx using our u substitution, right? So, if I want to replace the dx in terms of du, I do have to put in a factor of 1/2. Let me go ahead and put the 1/2 there. But other than that, this just becomes the integral of 3u squared. 3u squared. What's the antiderivative of 3u squared? Do that in your head. U, yeah, u to the third power. So this just becomes 2x minus 1 cubed. I'm just putting the u back in directly, which has to be evaluated from 0 to 1 here, right? And I'm running out of room, but that's okay. We'll finish it really quickly. So the only thing left here, guys, I'll just come over to this next board really briefly. So this just becomes the square root of 1/2. When I plug in a 1 there, I get 1 cubed. And then minus 1/2. And when I plug in a 0 there, I get -1 cubed. And that becomes just 1/2 minus -1/2, which is 1. So underneath this radical, I just literally have the square root of 1, which is 1. And that also checks it off. So this is a basis, which is also orthogonal and which is also consisting of unit vectors. So it is an orthonormal basis. What do you think? Does this make sense? It's a nice little warm-up problem. Does anybody have any questions so far? I can think of 2 questions if I was in your chairs that I would probably want to be asking. I'll tell you what they are. The first one is, Dr. Annan, how did you come up with this set to begin with? Like, where did this radical 3 times the quantity 2x minus 1 come on? It looks like you pulled it out of the sky somewhere and it just happens to work. But it's like, how would you have figured out that that's a good basis to have? So where do you come up with these orthonormal bases? Like, how do you make them? That would be one question that we should answer and will answer. By the way, the reason I'm asking these questions is because I'm going to answer these questions, right? So how do you get an orthonormal basis for a vector space? Honestly, if somebody was asking me to give a basis for P1 of R, the one that I would probably be thinking about is just 1 and x. Like, that's the most natural basis for P1 of R. It would be maybe even considered the standard basis for P1 of R. So it would be a reasonable question. It's like, why are you using this, right? And then how did you get this? So those are the 2 questions. So I want to address the question of why we would want to use that basis first. So this is just a little question I'm going to ask. So why is an orthogonal, and I'll put slash, orthonormal basis useful? Like, why would you prefer to use an orthogonal or an orthonormal basis? I mean, the thing about the 1 and the x up here, guys, the thing about this basis, as nice as it is, if you calculate the inner product of the basis there, the inner product of 1 and x, you're going to be integrating from 0 to 1 of x dx. And guys, that is not 0. I think it's 1/2. It's not 0. The point being that these 2 polynomials are not orthogonal. So it's kind of a bad thing, but the question is, why is it bad? Why would it be so useful to have an orthogonal or an orthonormal basis, right? On what planet could we be that this is a better basis than that? So I'd like to say a quick word about that. Why is it useful to work with a basis, even if it's messier looking? This is looking messier than the standard basis, but somehow this one maybe has some advantages. I'd like to point that out to you. So let's answer this question first, and then we'll talk about how I came up with that basis, because that's the other part of the story that I need to explain. So let's just assume that S, which is equal to the set v1, comma v2, comma dot dot dot, comma vn, let's assume that that is an, I'm gonna start with orthogonal. An orthogonal basis for some, just gonna make it some abstract vector space V. So imagine that you have any old vector space V and you have this orthogonal basis. What is so great about that? Well, let's suppose that we take a vector little v in that vector space. So I am currently grabbing any old random vector. So if I take any old random vector little v, question is, why is it good to have an orthogonal basis? Well, the first thing is, does everybody agree? Does everybody agree that I can write this vector little v in terms of the basis? Can I always write any vector from my vector space in terms of the basis? I sure better be able to. We spent 10 sections of chapter 4 talking about this, right? It's a spanning set. A basis is a spanning set. Every vector in V can be spanned by the basis. So I know that we can write my vector V somehow as a linear combination. I'm going to say C1 times V1 plus C2 times V2 plus da 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 plus Cn times Vn for some scalars C1, C2, da 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 up to Cn. Those scalars are to be determined. Can I write TBD? To be determined. So for some scalars that are to be determined, we know that this is possible. We know that this is possible. Guys, go ahead and put a box around this and let's put an asterisk on it. I want to refer to this equation a little bit. Okay, so we can write our vector V somehow as a linear combination, but of course I have to figure out what those constants are. How do we figure out what those constants are? Well, you probably remember in chapter 4 what we would have done. We would lay our bases down in the columns of a matrix, yeah? So we kind of make this matrix like so, up to V1 through Vn, and I would be augmenting that with one more column, and in the last column, normally you saw me putting like number symbols here in the far right column, but in this case, I'm not going to put number symbols. I'm going to literally put the vector that I'm interested in, which is V itself. Okay? And the unknowns of this matrix, the unknowns are the C1, the C2, and so on up to Cn. Those are the constants that are in this linear combination. Everybody with me? So we could do this. We could solve this matrix. We could do our EROs, get it into row echelon form, then go by back substitution through our work to solve for the constants. Yeah, we know that we can do that. And that would work. That would work for solving for the constants. But it would be potentially a big mess. I have to do a bunch of EROs. We know that that can be messy. Then the back substitution process, that could be messy. So it turns out that when you have an orthogonal basis, there is another way to get your constants without doing any of that. And I'm going to show it to you right now. What you do to come up with the constants in a clever way when there's an orthogonal basis in front of you is you take this boxed equation and you inner product both sides of it with, let's say, the ith vector. Okay, so watch this. I'm going to take the inner product so it'll be the inner product of something with Vi on star. So you'll see what I mean when I write it down. So what I'm going to do is I'm just on the left side, I'm going to have the inner product of V with Vi. And on the right side, I'm going to have the inner product of C1 V1 plus C2 V2 and plus da 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 plus Cn Vn with Vi. What is I, by the way? It's just any one of my random basis vectors. It could be V1, it could be V2, it could be V3. I don't really know. But all I've done is taken this box and inner product with VI on both sides of it. Yes.
Which is that supposed to be take,
You just whatever goes here.
okay,
I'm just leaving a little space there. Yeah, exactly. Okay, guys, we learned on Tuesday that inner products have nice properties. They respect addition and they respect scalar multiplication. This expression on the right side, using those axioms. Remember the 4 axioms of an inner product? Using those axioms, I can split this out. I can write it as C1 times the inner product of V1 with VI. And then plus C2 times the inner product of V2 with VI. And so on and so on. Somewhere along the line, I'll get to the ith term. I'll have CI times the inner product of VI with VI. I keep going. The very last term at the very end is going to be CN times the inner product of VN with VI. So what I've done, guys, is I've just taken this right-hand side and I've busted it out. I've split it all apart. Take the constants out in front. Split up the plus signs. All that's happened there. Again, what am I trying to do? I'm currently trying to figure out what are those constants. That's what we're gonna end up with as an answer here. Can somebody tell me what is the inner product of V1 with VI? The original vectors are orthogonal. If 2 vectors are orthogonal, what's their inner product equal to? 0. 0, right? This is a 0 right here, my friends. This is 0. And what's the inner product of V2 with VI? Also 0. That's also 0. See, these are all going to be 0. The last one, the inner product of Vn with Vi, that's also going to be 0. There's only one term that's not going to cancel out that way. And it's actually the one that I left here in the middle, because the inner product of a vector with itself isn't necessarily 0. It's only when it's 2 different vectors, right? Notice it says for I not equal to j, the inner product of Vi with Vj is equal to 0. So over here, most of these terms have a different subscript in the 2 slots, and those are all canceling out. But there's one term, which is this one right here, that is not canceling out. And do you see now that I can solve for C sub I? I can solve for C sub I. What is it? Well, the right-hand side, the left-hand side of the equation has the inner product of V with VI, and I'm going to divide by the inner product of VI with VI. Yeah. Without doing a single ERO, I have solved for the ith constant that is in this box equation. I want to write my vector in terms of a basis. This is a very common thing to want to be able to do in a vector space, and I can do it by using the inner product properties to solve for those constants here. And notice, by the way, when you take the inner product of 2 vectors, you get a number. So in the top here, this is a number divided by a number, which is just a number. That makes sense. These constants, they are all numbers. They are all numbers. And so all I'm trying to convince you of here is, what could you use an orthogonal basis to do? If the basis was not orthogonal, you couldn't do this. By the way, if the basis is actually orthonormal, then this denominator, did you guys notice? Did you catch this? This denominator is actually just the norm of V sub I squared, because it's the same vector twice. Well, if it's an orthonormal basis, that's actually just 1. That's actually just 1, which means you wouldn't even have this denominator. It would just literally be the part on top, even cleaner, even better. Right? It's even better in that case. You guys buying this at all? All right. Sometimes I don't think you guys are too excited about this stuff. But then again, I'm comparing your excitement to my excitement, and that's a tall order to live up to, because I have a very high amount of excitement about all this stuff. Get really into it. Yeah, anyway, you're not gonna see any homework on this or any test questions on this. I just wanted you to at least, we're talking about a topic. Well, why is Dr. Annan talking about this? It's because it does have a usefulness. And you can use it to, for example, help you work with these linear combinations when you're in the context of a basis. So I thought that would be worth showing you. But what I want to turn to next is how do you come up with an orthogonal or an orthonormal basis if you don't have one to begin with? Like if I'm working in P1 of R, this is probably the basis I'm going to start with. So how would I end up getting this basis, which somehow was better, out of that one? It's not clear. I'd like to show you how that works. If you guys are taking notes today, give yourself a nice big amount of space. I'm going to draw a diagram on this board. It's going to take the whole board, okay? To show you kind of how this all fits together. And I think it would be a good idea to write it down. So I will do it carefully in this space. So this is sort of I don't have a very creative title here. I'm just going to call this a process. And what you're basically going to do, guys, is you're going to start over here with V1, V2, and ... up to Vn. And this is going to be any basis for V. Any basis for V. And I'm about to explain how you can take any basis for V and replace it with a better basis, which is going to be W1, W2, ... up to Wn. And this is going to now be an orthogonal basis for V. So how can we take any old average basis for V and turn it into an orthogonal? The name of this process that we're going to illustrate in a minute is something called the Gram-Schmidt process. It's named after the two mathematicians who independently discovered this. So they both get credit for it. It's a hyphenated name involving those two mathematicians. Now, if all you want is an orthogonal basis, once you've applied the Gram-Schmidt process, you'll have it. You'll have it. By the way, this notation is not in the book either. So I tried to make it streamlined to be a little easier, so it's not as technical. So you really should think about writing it down, or at least taking a picture of it when I finish drawing it. But it might be that we actually want to create an even better basis than just an orthogonal one, which would be to proceed to an orthonormal one, which is an even better basis. So that would be another process that would lead us, let's say, to U1, U2, and ... up to UN. And over here, now what you're looking at is an orthonormal basis for V. Yeah, and how do you go from any old orthogonal basis to an orthonormal one? Well, the name of the process here is normalization. And I think you guys should already know what I'm talking about for that. Can somebody tell me? Because you would have done this even in Calc 3. How do you normalize a set of vectors? I do this in engineering all the time, so you've got to know how to do this. I know you know how to do this. Levi?
You just turn it to the normal vector by dividing by its magnitude.
Dividing by its norm or its magnitude. Exactly. You just take each vector and divide by its norm. We actually did that, I think, on Tuesday. So you just take the vectors and you divide by their norm. Let's write it down. So for this, what you're doing, guys, is u sub I. You're just taking the double u sub I and you're dividing by the norm, or the magnitude is the other word, of that w sub I. That's exactly right. That's exactly right. So this normalization part of the diagram shouldn't really be anything new, because you would have done that in Calc 3 pretty regularly. But what probably is new for you is the left part of the picture, where we're taking our random basis and we're making it orthogonal. So I'm going to explain that process on this board right now. Questions about that diagram at all? Everybody kind of get I just want you to have the big picture, what we're doing. And then we're just gonna describe this process, then we're just gonna do a couple of examples, and that'll be it for chapter 5. We're almost done with chapter 5, guys. We just started it on Tuesday. We're finishing it today. Man. That's really, well, part of that is the videos that you watch. So we'll say we started it over the weekend. We're already finishing it today. It's a short chapter. How does the Gram-Schmidt process work? That's what I want to put on this board here. Gram-Schmidt process. What you need to do, guys, is you need to replace the V's from the random basis with the W's. So here's how you do it. The first vector for your orthogonal basis, you literally just take the first vector from the original basis. You don't need to tweak it at all. You just take that same vector and just go with it. Okay, that's W1. Now I have to give you the formula for W2. Now, and then in a minute, I'm going to also give you the formula for W3. Guys, leave some room here. I am actually going to put those formulas down in a minute, but I'm going to derive them. Or at least I'm going to derive the one for W2, right? I don't like just throwing the formula on the board with no reason. That's like driving the car and saying I'm an expert on cars because I can drive the streets, but I have no idea what's going on underneath the engine. I don't like feeling like that with math, so I want to understand these formulas. Let me show you with a picture. Let's suppose that V1 is here, and let's suppose that V2 is here. And there's some angle between them. I'll call it theta. And of course, we don't know that theta is 90 degrees yet. It's not an orthogonal basis yet. So this is just any old random angle here. And I would like to replace V2. Well, first of all, V1 is just going to be W1. I don't have to tweak that at all. But I would like to replace V2 with a vector that is orthogonal to W1. And there's an obvious candidate for that, which is if you just drop a perpendicular here, we're gonna do a little geometry, guys. If you just drop this perpendicular right here, this vector here, I'm gonna draw it in red, that red vector would be a great choice for the W2. Because notice that now W2 is perpendicular to W1. Okay? So that is the picture of the vector we want, but what's the formula for it? Because I want to write down the formula for it here in a minute. Well, it turns out the way you get the formula for the red vector is you draw another vector, which I'm going to draw here, guys, in blue, which is actually what's called the projection. So this blue vector is the projection vector. It's the projection vector of V2 onto W1. It's the projection vector of V2 onto W1. Basically, you're smashing the vector down onto the direction of the V1. If the sun was shining in the sky way up above the ceiling, shining down on this, the shadow of V2 would be this blue vector that's pointing along the direction of the W1. Okay, great. So this blue vector is the projection vector. I'm going to use this notation, guys. P of V2 comma W1. Actually, let's put it over here so I have more room. P of V2 comma W1. And I would like to figure out the formula for it. Would you guys all agree that V2, that this projection vector is just parallel to W1? It absolutely is. So watch this. Watch what I'm going to do. Give yourself a little bit of room if you're writing this down. W1 is the vector that we see in black. I'm going to first shrink it down to being a unit vector. So I'm going to take the big black vector, I'm going to shrink it down, so now it's really short, and then I'm going to stretch it back out to be exactly the correct length. Can somebody tell me how long that blue vector is? So I took the whole big huge vector W1, I shrunk it down to being a unit vector. Now I'm gonna pull it back out to be exactly the right length. Would you guys agree that the length of that blue vector is simply the hypotenuse of this triangle times the cosine of theta? Am I allowed to do trig in this class? It's supposed to be differential equations and linear algebra, and I'm gonna do a minute of trig with you. It's just the trig, right? So it's just the hypotenuse of that triangle, which is the norm of V2, times the cosine of theta. So the cosine of theta gives you that, base length right here. Okay. Now, the thing is, we have a formula for the cosine of theta, which I hope you guys remember, but I will remind you if you don't. Basically, you're going to take the norm of V2, the cosine of theta, if you remember from the video notes or even from Tuesday, it's the inner product of V2 with W1 divided by the norm of V2 and the norm of W1, yeah? This is the cosine of theta, and then I still have a 1 over norm of W1 on the bottom, and then finally my W1 vector itself is over here on the end. This is just W1 being stretched out. All of this is just a scalar. It's just being stretched out numerically to be the right length of that blue vector. I love it. And if you kind of look at the math of this, the norm of V2 ends up canceling the norm of V2 here. And we even can clean up the denominator a little bit. Sorry, I'm going to squeeze this down here, guys. The numerator here is the inner product of V2 with W1. And on the bottom, do you see that on the bottom I have the norm of W1 twice? Well, that just means we have the norm of W1 squared, right? And then the W1 vector on the end of that. Have to be very careful. The one thing about this you have to be careful about is make sure you don't get numbers confused with vectors. So the only thing here that's the vector is the W1 that's way out on the far right side. All this stuff with norms and inner products, those are all just numbers. Those are all just numbers. So guys, this is how much we have to stretch the vector back out so it's exactly the length of the blue vector. And I'm basically done with my derivation. What am I deriving? I'm deriving a formula for W2. Look at your picture. Would you agree that the blue vector plus the red vector gives you the hypotenuse? I think so. It's just a triangle, right? So the hypotenuse is V2. And if I want to solve for the red vector, if I want to solve for W2, I'm going to take the V2 and subtract the blue vector. So it's just, here's the formula, it's just V2 minus, so it's the hypotenuse minus this thing we just derived in blue, which would be the inner product of V2 with W1 divided by the norm of W1 squared times W1. That's the formula. With a derivation to go with it. And I won't do the derivation for W3, but same idea. It's just that you start now with V3, and now you start subtracting off. First, you subtract off the inner product of V3 with W1 divided by the norm of W1 squared times W1. But you have to keep going because you also have to subtract off the projection along W2. So then you also subtract the inner product of V3 with W2 divided by the norm of W2 squared times W2. And of course, this could keep going for however many vectors you had. So I'm going to, well, first of all, I'm going to ask, is there any questions so far? SF?
Would this still work the same if V2 was longer than V1, so the projection of V2 is longer than W1?
Yeah, it turns out that doesn't even matter. Yeah, it's a nice thing. This argument goes through either way. Yeah, good question. Anything else? So I'm going to give you guys two pieces of good news right now that I think is going to, both of these things are going to make you happy. The first one is I am never going to ask you a question where there's more than 3 vectors. So this dot, dot, dot part here, you're never gonna need it, because I'm never gonna ask you to do this with more than 3 vectors. The other bit of good news is that when we take our exam, which is next Thursday, these formulas will be right there on the front of the exam. So you don't need to memorize these formulas. You just really, you know what the hardest thing of the Gram-Schmidt process is to just make sure you know when it is you're supposed to be using it. Well, once you actually are using it, it's really plug and chug. Like this is just, it looks messy, but these are just inner products and norms, which just comes from some formula. So it's actually not so bad. Let's do an example. I'd like to show you how it actually plays out on an example. It's messy, but it's conceptually very straightforward. Let's try an example. Okay. If we're doing good on time. And this is it for chapter 5. I just need to show you this Gram-Schmidt process in action, and then we have covered all of that material. So let's just do this one. All right, here's an example. Let's find an orthogonal basis for I'm going to make my vector space V is going to be the span of, and then I'm going to give you the vector -1, 1, 1, 1. And the second vector is going to be 1, 2, 1, 2. Let's take that. First thing I want to ask you guys is, before I can find an orthogonal basis for a vector space, I have to come up with a basis for the vector space, right? The diagram starts over here. I have to have a basis for V in the first place. Anybody have a guess as to what my basis for V is here? And it's not a trick question, by the way. It's the only thing you could tell me, because it's the only thing I got on the board, which is those 2 vectors. These 2 vectors, they are a basis for V. Can I explain why? This is, in other words, these are going to be my V1 and my V2. I'm going to explain why real quickly. They are not scalar multiples of each other, so they are Li. Remember, a basis has 2 things. I'm just reviewing for the next week's test. A basis must be Li and must span V. Those vectors are Li because they are not scalar multiples of each other. I only have 2 vectors. As long as they're not scalar multiples of each other, they are Li. Now, why do they span V? They span V because V is equal to their span. That's the way the vector space was created. A set of vectors will always span whatever they span, yeah? They will always span whatever they span. So in this case, the vector space was constructed to be the span of those vectors. So by default, they are a spanning set. Are you guys following that? That argument comes up a lot. Whenever you form the span of anything, you always get a subspace, and the vectors that were doing the spanning, they are a spanning set for whatever you have. So they're a spanning set and they're Li, so they are a basis. Okay. They're not a basis for R4. You can probably recognize these are vectors that are part of R4. If I really wanted to have a basis for R4, I would need 4 vectors. I only have 2 vectors there. So this is not going to span the whole R4, but it does span whatever it spans, and that's what V is. Okay, great. I think I've hit that point enough. So let's go on, and let's actually start doing the Gram-Schmidt process. If you're taking this exam next week and you're like, I don't really have time at the moment to go through it all, if you just would do me a favor, if you can see that you are in a problem where you need to use the Gram-Schmidt process, write that down. Even if nothing else is on your paper, you're going to get a couple of points for just writing this down. Because, yeah, based on what the question is asking, you grabbed the correct tool out of our bag of tools. And I like to know that, and that's worth something. So write it down, Gram-Schmidt process. So that's what we're gonna do. So the W1 vector is just equal to the V1, so negative 1, 1, 1, 1. Okay, so that's the W1. And then for W2, this one we have to work a little bit. The formula for W2 is we just simply take V2, which is the vector 1, 2, 1, 2, and I'm going to subtract. Now, what I like to do is just kind of build myself some parentheses to make this fraction here. And then I put my W1 vector back on the end of that. So this is just formatting it into this shape here. V2 minus some fraction of W1. That look all right? Now, what goes in the numerator? The numerator is the inner product of V2 with W1. So here's V2, and this is actually also W1. So they're right next to each other, and I could just dot these together. By the way, I'm using the standard dot product, right? They didn't give me any other weirdo inner product formula to work with, so we got to just use the standard dot product. So negative 1 times 1, that's negative 1, plus 1 times 2, plus 1 times 1, plus 1 times 2. So it's just 1 plus 2 plus 1 plus 2. Okay? And then in the denominator, we have the norm of W1 squared. So what is that? That's just the inner product of W1 with itself. So you're dotting this first vector just with itself. Negative 1 times negative 1, plus 1 times 1, plus 1 times 1, plus 1 times 1, right? So it's just negative 1 squared plus 1 squared plus 1 squared plus 1 squared. That's the norm squared for W1. And actually, if you do the math on this, you have 4 here on top and you have 4 on the bottom. The numerator and denominator just cancel. So this guy cancels with this guy. And all you really have to end up doing is subtracting these two vectors. So you take 1 minus negative 1, that's 2. And then 2 minus 1, which is 1. And then 1 minus 1, which is 0. And then 2 minus 1, which is 1. There's your W2 vector. And so my orthogonal basis, we're already done, guys. It's just that easy. Your orthogonal basis is just the set of the W1 vector, which was the same as the original V1, and then the W2 vector, which is 2, 1, 0, 1. You guys with me? It's purely computational. I'm making this even easier because I'm just going to give you these formulas. You don't even have to memorize this formula. So it's pretty straightforward. By the way, you can, of course, check your answer. If you dot these two vectors together, you had better now get 0 because these two vectors are supposed to be orthogonal at this point. So if you did the dot product of the two things you ended up with, you could confirm that it is 0. Yeah. Just as a follow-up, let's suppose we wanted to go all the way to an orthonormal basis. This question was asking about orthogonal basis, but let's just add that here as long as we're on a roll. Follow-up. On the follow-up, all I want to know, guys, is what is, I won't even write the question down. I'm just going to go straight to putting the answer into the place here. I would like to write an orthonormal basis for the same problem. So remember how this works. You're now looking at your orthogonal basis and you want to move over here to the orthonormal basis. All you got to do is normalize those vectors. Divide by the norms of the vectors, right? So let's just do it. We can do this one, I think, almost without showing any work. I just take this first vector and I divide by its norm. What is the norm of this first vector? Well, we have our norm formula, which I hope everybody is memorizing nicely by now. It's the square root of the inner product of that vector with itself. This is always the norm of any vector. So I just need to know what is the norm of this vector. It's the square root of dotting this thing with itself. If you dot this with itself, we already did that once already. We got 4. So it's the square root of 4. All right, so my u1 vector is basically the w1 vector divided by the norm. The norm is the square root of 4, which is better known as 2. Okay, and then what about my second term here? I take the 2, 1, 0, 1, and I have to divide that one by its norm. Its norm will be the square root of 2 squared plus 1 squared plus 0 squared plus 1 squared. So that's 4 plus 1 plus 0 plus 1, which is 6, square root of 6. That's the answer. Make sense? Seth.
Is it okay to leave our answers like that, or do you want us to distribute?
Oh, I forgot to mention that. Yeah, somebody in my first class asked me the same thing. If you want to put these 2s inside the slots and turn these into 1/2s, you can. But I'm okay with it written just like this. Same thing here, these radical 6s, you can shove them up underneath the individual slots if you want, but you don't have to. Also, guys, you don't have to rationalize these. Do the high school teachers still do that? Do they still say stuff like, oh, simplify the square root of 30 over 6? And then they make you do it, especially if there's like something down here or whatever. See, I'm fine with leaving it like that. You don't have to simplify, just leave it like that. It's not important to clean that up. Certainly not the main point of this class. Okay. Yes, Ryan.
So if we noticed like the second vector or like something with the computation would be easier, could V1 be the second vector and V2 be the first?
Oh, another great question that I also mentioned this morning. Maybe after lunch, I forget things more easily. I seem to forget some of the things I want to say. Yeah, the question was, what if we call this vector V1 and this vector V2? Oh, that would not be wrong. That would not be wrong. And you would end up with a different W1 and W2 than what I did. But as you guys are very well aware, there are many correct answers for a basis, for a vector space. So when you get questions like find a basis, you shouldn't be worried about whether your answer agrees with everybody else's answer. Because it's certainly possible to get different answers. And that would be the fastest way to get a different answer, would be to just switch the order of your vectors. Because then your W1 would have been this vector, right? Which isn't even one of the vectors we ended up with over there. So yeah, it would be a different outcome. The only thing about bases that is compatible is the number of vectors, right? So this is 2-dimensional. V is 2-dimensional. So anybody else working this problem would have to get 2 basis vectors, just like we got 2 basis vectors, but they could be different. They could be different vectors. That's very true. Okay, I'd like to do one more example where it's not just the regular dot product. The dot product is a little like too standard. Sometimes we do have to work with these other vector spaces. Even in the engineering world, they come up. So I want to show you how it might look on a problem where you have some different vectors to work with. So let's do one more example and then we'll take a break. Okay, so here we go. Example. Find an orthogonal basis for V, which is equal to the span of 1 x squared and x to the 4th, where, okay, on a problem like this now, guys, at this point, I must tell you the formula for the inner product. There is no one standard formula anymore, so I have to give you the formula. So I'm going to do it right here. The inner product of f with g is just going to be the integral. This time I'm going to use limits from -1 to 1 of f of x times g of x times dx. And those limits of integration are critical. They are critical in the sense that you can take things from being orthogonal to not being orthogonal just by switching the limits. You can take something from being a unit vector to not being a unit vector by just changing the limits, right? So it's actually really important that those limits are given in the problem. And this particular inner product is very related to the solution to a differential equation that comes up a lot in the real world. So we're going to use the limits of -1 and 1 on this example. Let's get into it. Let's get into it. Oh, by the way, I want to go back to Ryan's question. Ryan was asking me, could I switch the order of these vectors? In other words, the way I've got it written right now, here's V1, and here's V2, and here's V3. And what I just told Ryan, which was true, is that you can switch the order if you want to. But I did want to say one other thing. When I'm giving you these problems in the homework or on a test or anything like that, I'm probably going to be giving them to you in the best possible order. Don't, for no reason whatsoever, switch them around. Because what will happen is the calculations will be much worse. I will probably try to set it up so that if there are messy numbers, at least they don't come into it until the end. Right, so I would always recommend just whatever order they were given to you in is supposed to almost be a hint. Use that order. Okay, so we're going to do that here. W1 is just going to be equal to what? It's equal to V1, which is 1, right? There you go. That's the first vector. Write that down. And again, guys, if you're taking the test and you're running out of time, at least tell me that. If you write that down, I can give you some points for it. It's not the hard part of the problem, but I can give you something. Right? It takes like 2 seconds. Okay, what about W2? W2 is equal to V2, that was x squared, minus some fraction, which I'm going to fill in a minute, times W1. So we'll fill in this fraction. The numerator of the fraction is the inner product of V2 with W1. Well, that would be the integral from -1 to 1 of, let's see, V2 is x squared and W1 is just 1. So it's just the integral of x squared, dx, evaluated from -1 to 1. And in the denominator, we have the norm squared of W1. Well, that would just be the inner product of W1 with itself. That's the integral from -1 to 1 of 1 times 1 dx. Okay, and let's go ahead and work out these integrals. I'm going to go kind of fast on the integrals portion of it. The integral of x squared from -1 to 1, you'll get what, 1/3 of x cubed, and you'll evaluate that from -1 to 1. It comes out to 2/3. And then on the bottom, when you just integrate dx from -1 to 1, you end up getting 2. And then all of that is still times 1. And so the answer here is just x squared minus 1/3. That's your second vector. That's your second vector, x squared minus 1/3. Okay, great. I'll come over here to do the W3. So this time we actually have 3 vectors to do. Oh, by the way, I don't know if you guys, did you notice that, so the norm of 1 down here on the bottom, actually it was 1 squared. It turned out to be equal to 2, given this formula. So if I integrate 1 times 1 from -1 to 1, I actually get 2 for an answer. Now, that means this is not a unit vector. There's no problem with that. I'm not asking for a normalized vector right now. But just so you know, this is not a unit vector. Now, if the limits of integration were 0 to 1, well, then when you evaluate this integral of 1 times 1 from 0 to 1, you would have gotten 1. So all I'm trying to say is just changing these limits of integration will change everything. It changes what's a unit vector. It changes what the angle is between vectors. It changes the norms. It changes the inner products of any 2 vectors. So it's very, very easy to sort of screw up a problem by just changing the limits of the integration. All the calculations change. Yeah, but we're gonna live with the one that I've given you here. So far, so good. We're 2/3 of the way done. Unfortunately, W3 is the worst one. As you can see from the formula, it gets messier as you go. So for W3, I might skip a couple of the integrals and just have you take my word for it. But W3, according to my formula, it should be V3, which is x to the fourth, minus some fraction multiplied by W1, and then minus some other fraction multiplied by x squared minus 1/3. So just getting it formatted, it would shake out like that, and we just have to put everything I'm going to fill in here, guys, is just an integral that has a number for a value. It's just going to be some numbers. The first integral upstairs, that's just this one right here, the inner product of V3 with W1. Well, what is that? The inner product of V3 with W1 would just be the integral from -1 to 1 of x to the fourth, right? Integral of -1 to 1 of x to the fourth dx. The denominator here is actually the same as the denominator we had earlier, which was just the integral from -1 to 1 of 1 times 1 dx. And then the integral upstairs here, that's this guy. The inner product of V3 with W2. Here's W2, and here is V3. I have to take the inner product of these two things. Let's write it down. It's the integral from -1 to 1 of x to the fourth times x squared minus 1/3. By the way, to do that integral, you're going to need to multiply it out and then do the antiderivatives. It's a little bit of a pain. But we'll come back to that. On the denominator, I have the integral from -1 to 1 of what? The norm of W2 squared. In other words, the inner product of W2 with itself. Right? So that just becomes x squared minus 1/3 squared. That's the inner product of x squared minus 1/3 with itself. This is all just plug and chug. Plug and chug all over the place, guys. It could be very easy or it could be very boring, or maybe both. So let's just see what this comes out to. We get x to the fourth here, and then I am going to save you the time of doing the integrals. You get a 2/5 on top and then a 2 on the bottom times 1. And then these last integrals are really bad. The numerator is 16 over 105 divided by 8 over 45, all times the quantity of x squared minus 1/3. I'll leave it to you to confirm those values if you're interested in it. It's not really the main point here, but we end up with x to the fourth minus 1/5. And then if you clean up 16 over 105 over 8 over 45, I'll let you check that. It comes out to 6 over 7, actually. It's quite nice. Times the quantity of x squared minus 1/3. And you could leave it like that for the W3 if you wanted to. That would be fine. So your final answer then? Final answer, we'll write it down, guys, then we're going to take a break. Your orthogonal basis would be, what was W1? 1. And then the W2 was x squared minus 1/3. And then the x3 was, or the W3 was x to the fourth minus 1/5 minus 6/7 of the quantity of x squared minus 1/3. Just like that. That'd be the answer. Yay. You okay? Too bad? And we've already explained earlier today why we might prefer this basis over the original one that was given. Somehow having an orthogonal basis could be actually an asset that helps us out with working in that particular vector space. Yeah. So. Okay, I think I've said everything I need to say about all this stuff. Let's take a 10-minute reprieve. Go ahead and stretch your legs. If you want to get some water, step outside. It's hot out there if you go out on the balcony, but feel free to do so. No, I just thought. Oh, yeah.
Yeah. I've been with that coach for a long time. So,
I gotta say, I just did it.
yeah. You say I wish.
No.
But like.
She's so sick, she's so sick. Except for the minor course. He was like, yeah.
Oh, yeah.
Our short is from here, but some of it is from here. So I usually cut through the business goal. Yeah, so I'm going to cut.
Right? Your neck walks.
Very. This is other.
Yeah.
It's been excellent. That was me.
So you're gay. Kayla plays so
I can't miss it. Meters on the
Reading now, you can only have one. Yeah, she's been. Things like that.
Well, that's
I
not
can fix
bad.
her.
That was not
That and do like that. Yeah, you're right. I think
bitches.
we have corridors, and I was like.
Well, that's.
Because I was finding that I was over my mom, but I should see my shoulder. Oh, man. Like, wow, bro.
So you're like over.
Yeah. But I'll show you her. Bro.
I'll sleep. Eat there. I can really sit. So it takes sounds like. So. It was said, like, it was like, like, control. Right, I'm not sure which one it is, but. It's not.
Gotta try everything. Oh, that's fine.
Really?
That's just like, have to be a minute.
Yeah.
That's.
It's actually.
Serious. This is high. I'm glad you got some rest.
No.
Yeah, well, I've been having to eat.
You're not gonna sit here, bro. I'm just greedy, like.
I don't know if I can last.
Survived two at that same by two. Right.
No,
Five,
I-
three, and five. Everyone that's 5, and 8 look the same. Yeah, so you're like, it's like these 5 minutes.
Yeah, for sure, for sure.
You know what worries people of what?
That's just some-
I got the one of this. And one of the side of that. Like that. You definitely have back girl like that. But I think that's. Yeah. And then he's like, let me start actually stop something. Is that not you really?
She's like, no, you're just handshake. Let me handshake, not the other thing.
Like I wouldn't take that. So like that's small. I have like a very nice to be on. But yeah, sorry. My only go to being on. It creates the almost out of. No. Like created another. Like I actually got these two people that before I wasn't capable of honestly. Like I don't understand it.
All right, guys, I think, it's been about enough time, for people to, what is that you got back there? Oh my gosh. Pretend I didn't see that. That's okay, you don't have to, never mind. You're off the hook. Let's go ahead and get started. We have like less than a half hour left. I just want to tell you what we're going to do for the rest of the class today. I'm going to start by talking about our midterm, which is next Thursday. I'm going to give you the heads up on that and kind of some of the highlights of what I think you should be thinking about. And then I think I promised you that this homework number 12, which is really based on section 5.1. I actually took away the submit link on Canvas. You can't turn it in, even if you tried to. So we're going to do some of the chapter 12 problems together just for practice, just kind of as part of our class time. So I think we'll do that. And then that will probably kill the rest of our day today. We are done with chapter 5. So there isn't really anything new to talk about with that. But let's talk about this exam coming up. It says it is just next Thursday, so midterm 2. It is next Thursday, which is actually March 19th. And like last time, you'll have the entire 2 hours to take the exam. There won't be anything else to do. You can stay as long as you need to during that 2-hour stretch. It is going to cover. Well, the big one, guys, is this chapter 4, which has 10 sections. Now we did skip. We skipped section 4.7, so you won't find anything to look at for that. But the rest of that chapter, we did the whole big long thing. And so this is going to be, I'm just going to guess right now. I obviously haven't written the test yet, but I'm going to guess it will be more than half of this midterm is going to be on chapter 4. Things like subspaces, spanning sets, linear independence, basis and dimension, the rank nullity theorem, row space, null space, column space, invertible matrix theorem. If you're trying to write all that down really fast, don't worry, because it's all typed up for you in the handout I'm going to show you in a second. But there's a lot of stuff in this chapter. There's a lot of stuff there. Then we're going to have chapter 5, which was much shorter. This was just 3 sections, which we just finished basically this week. 5.1 through 5.3. This is maybe going to be closer to like maybe 30% of the exam next Thursday, approximately. And as you can see, this does not quite add up to 100%. And that's because there is one more section. It is 6.1. This might be approximately 15% of the exam. I don't know exactly. Now, here's the deal. I have not covered 6.1 yet. I'm going to devote all of next Tuesday to covering section 6.1 and doing the homework from that section. So there will be a homework to turn in next Tuesday, but we're gonna basically do it in class. So you have sort of two choices with this 6.1 section. If you're okay, if you don't want to worry about it until next Tuesday, that's one approach. You can just say, all right, he told me he's gonna cover it on Tuesday and do all the homework. That's fine. If you're the type of person who doesn't feel like you can see it on Tuesday and then do a test on Thursday, as it's just 48 hours in between, then there is another option, which is that I have videos that cover that 6.1 section. And what I'm going to do is send you an email, and you can choose if you want to watch that sooner. Like you could watch it tonight if you wanted to. It's a new chapter, it's a new topic. So it's about linear transformations, but I want to get that started, and I want to have it on this midterm. So anyway, that's the only thing that's kind of bad, is that I didn't quite get to this yet. I'm just going a little slow this semester. I don't know why, but I'm gonna ask you to learn this section. We'll do it on Tuesday. Full blast. I promise I'll cover everything. And also, oh, that reminds me also, I forgot to mention the review sessions. I will talk about 6.1 during the review sessions as well. These are also 100% optional. You do not have to come. You can ignore everything about this. But I had some students ask me if I would be willing to come in and do an in-person review session, and I'm going to do that. On Sunday, I'm going to be right here in this room, and we're going to do it from 3 until 6 p.m. Now, it's probably not going to take 3 hours. I think it'll be more like 2 hours with some change maybe, but I just decided to call it 3 hours. You can come late, you can leave early, you can not come at all. I will be recording it, and then I'm going to YouTube it and send it out to everybody. So if you would rather watch it on YouTube, you can. But I have a lot of students who tell me that that doesn't work so well, that they just don't focus as good when you're kind of sitting at home with a bunch of distractions, watching it on a screen. So if that's you, and if you know that that's you, and that you could probably use the review session, I would encourage you to come down on Sunday. You can probably park right next to the president of the university's spot, because there won't be anybody else here on the weekend probably. It will be a nice, easy commute to do that. Alternatively though, I'm gonna repeat the same review session on Wednesday evening. The only reason I'm doing this is because I don't think 70 students can all come at one time. Like, you're not all gonna be available at the same time. So I'm just gonna offer 2 different times. And this one, unfortunately, I doubt that this room is available. So we're gonna do it down close to my office in the basement in MH47, okay? But they're gonna basically be the same, okay? On Sunday's review, I probably will kind of explain a little bit of the 6.1, because you'll see some of those questions I'll be practicing. The way the review is going to be, guys, I'm just gonna be doing a bunch of practice problems. What I'll probably do actually is grab an old midterm and just go through it. Like, just kind of go through those problems from the exam. Speaking of old midterms, if we look in the Canvas resources folder again, just like for the last test, under files, there is a folder here. It's a little hard to read probably. It says midterm 2 resources. I'll open this up, and again, I'm going to remind you, as I did with the first exam, that nothing here is required. This is all optional. I don't really expect anybody, unless you really don't have anything else going on, nobody's going to have time to do all of that. But I just want to highlight a few things that you can do. There's a sample midterm and then another sample midterm. I have 2 of them here, along with the solutions. So I would try to practice it without the solutions, see how you come along with that, and make notes of where your weak points are as you're going on. So, okay, oops, I need to remember how to do the angle between 2 vectors. Or, oops, I need to remember how to find a spanning set. Like, whatever it might be that you need to review, make little notes. But there's 2 samples. One of them is all capitals, the other one is all lowercase. And again, even though the solutions are posted here, you're also welcome to come to my office if you want to ask for my help directly with how to think about some of these problems, okay? Because I want everybody to do well. I'm going to be around next week a lot, so not even need to worry about it. I also have these review sessions in here. Now, more than likely, you can ignore those, especially if you're coming to this review session, then you don't need to like see another review session, but there is a review session document in here. And then there's also this this review handout. Let me just open this one up for a second. The midterm 2 review handout, it comes up here. You know, it's got all this stuff at the beginning. The coverage of topics, look at that. Look how big chapter 4 is. That's all of the words from chapter 4, and then chapter 5 is much smaller, and chapter 6 is even smaller. So that's just kind of an overview. But I almost sometimes think it's more helpful to look at this bullet point list, things to be able to do. And then I have an entire big long list here of stuff to be able to do. So just to point out a couple of examples, you probably can't read it very well. Know and be able to use the rank nullity theorem. Be able to find a basis and dimension for a vector space. Be able to verify the axioms of an inner product. That's the stuff we've just been doing this week, and so on. And you will find that there's 3 or 4 bullet points at the end that has to do with the stuff from 6.1. So you're not quite, you know, primed up yet for quite the end of the list, but there's a lot of carry out the Gram-Schmidt process. Okay, well, we just learned that like 20 minutes ago. Be able to find the norm of a vector, the angle between 2 vectors. And then some of the stuff from chapter 6 is there too. But I like using that bullet point list, just go through. And then if you come to some item that you're like, ooh, okay, I don't remember what that was about, or I'm not sure I can do that, or I need to review it, make yourself those notes, right, as you're going along. And that way you can go back and review it. Also, there's a bunch of practice problems in here as well. So there's like 8 or 9 problems, I think. And again, nobody's going to have time to do all of this stuff. I mean, probably nobody's going to have time to. I had time to, but I've also been doing it for many years. So if you need more problems, if you do both sample tests and you come to the review session, you're like, I still want to practice even more, you can find even more practice here as well. Okay, so that is, in a nutshell, the overview for the exam. The solutions to these practice problems are also in, they're right here, midterm 2 review solutions, the very top document there. Yeah. Okay, so there's a lot of stuff in here. And again, pick and choose, do what you have time for, and then let it go from there. You can be a very, very good student and not have had time to do all of this. That's perfectly possible. I understand that. It kind of just depends on yourself. Like if you're getting all the material, feel really solid on it, maybe you don't have to go through hardly any of it. You know, it just kind of depends on where you're at. You can also come by my office. I'll pop quiz you on a topic. I'll be happy to do that. My office hours are pretty quiet lately in the last couple of weeks. So that's good in a way. It means there's plenty of access. All you got to do is come in and meet me halfway. I definitely want people to do well, and I'll do what I can. But I also won't force people. You know, I'm not gonna be the type of person that's gonna be upset if people don't come. But you know, I do like it when people come, especially when we get close to the midterms and people want to kind of put it all together, or even just to listen to other people's questions, or just to be disciplined. Sometimes when you're hanging out at school, it's less distracting for some people. They've told me this, right? That just being on campus kind of helps. So I'll be around a lot. I'll send out over the weekend. I have my, my weekend email that you'll get, and it'll have a summary of all of my extra hours when I'm going to be around. So for example, normally I don't have office hours on Wednesdays, but this next week I will, because the test is on Thursday. I'll come in and spend extra time just to be available. And if you end up not needing the time, it's fine, but I just want you to know that it is available to you. Okay? Any questions about any of that? I don't think we're going to need the table of integrals this time. I mean, I might put it in the exam, but I don't think we're going to need that. I'm going to give you those Gram-Schmidt formulas, but aside from that, it's less of a calculation heavy section. For the most part, this is checking subspaces and spanning sets and basis and stuff. There's really not a lot of formulas. It's more about just knowing the processes, the procedures that you need to use to do those things. So yeah, I would recommend over the weekend that you start on studying for the midterm. And if you do decide to let the 6.1 wait until Tuesday, that is okay. there's plenty else here that you can start getting ready for. And, it should be all right. As far as the homework goes, that was the other thing I was gonna mention. So homework number 12 is the one where I've written some of these problems on the board. We're gonna do them right now. You're not turning these in, so there's nothing to worry about with that. The next homework is number 13, and this one is due actually on Friday night, which is just tomorrow night. But it is just the Gram-Schmidt process, the computational stuff we were just doing before the break. It's not too conceptual, it's just cranking out calculations. I'm going to have office hours tomorrow, like I always do on Fridays, after 8 o'clock. So feel free to stop by in Zoom or in person if you do need some help with anything there. But I have a feeling that this one is just practicing the stuff on inner product spaces. And then after Friday's homework is done, homework 14, this is the one that's on section 6.1. This will be due on Tuesday, next Tuesday, but keep in mind that I'm gonna do it mostly in class. So you won't have to work too much on that. If you don't want to work on it at all over the weekend, don't worry about it because I'll do most of that for you in class. Okay. And that'll be it for getting us up until the exam. Question, Ryan.
So is everything other than the formula for the Gram-Schmidt process on us to know any formulas?
Yeah, you'd want to know any of the other formulas. So you'd probably want to know the inner product axioms. We're going to review that in a second. The formula for the cosine of an angle, the norm of a vector. There's a couple formulas like that you'd want to know. I think chapter 4 really doesn't have that many formulas. There's the rank nullity theorem. I guess that's a formula. Yeah, so there are a few things like that that would be good to write down and just review. Okay. All good? I'll turn off the screen here. Let's spend what time we have left, about 15 minutes or so. I just want to solve a few more of these problems that are actually on homework 12. I did a bunch of them already, guys, on Tuesday. In class on Tuesday, I did a number of these problems, but let's just do the ones I didn't do on Tuesday as much as we have time for in 15 minutes. And then we'll just leave it at that at whatever point we get to. So here, these are all coming from chapter 5. We're still looking at inner product spaces. And the problem here, number 1, just says find the angle between these two vectors. What universe do these two vectors live in? Somebody besides Gabriel and Levi. I've heard from you too, but I'm not asking anything too crazy. Which vector space do these live in? How many slots are there? 5 slots, right? So that would be R5. This is the vector space R5. They did not give us an inner product here to use, so we're just going to assume that we're going to use the standard dot product to do this problem. And the angle would be represented using this cosine of theta formula. And so just make sure you know how to do this. This is actually the same formula from Math 250A, guys. This should be something everybody knows. The cosine of an angle, it is the inner product of the vectors v and w divided by the norm of v times the norm of w. That's what we're going to have. And we're just going to use the dot product to calculate this. So the inner product of v and w, the dot product here, 0 times -3 plus -2 times 1, 1 times -1, 4 times 0, plus 1 times 3. Just add it all up. So it's -2 plus -1 plus 3. It's actually 0 on top. And if it's 0 on top, I don't even care what's on the bottom. As a fraction, that becomes 0. Yeah, that becomes 0. And so the cosine of theta is 0. Actually, that tells you that these vectors are actually orthogonal. They are actually orthogonal because the cosine of the angle is 0, meaning that theta is 90 degrees. If I ask you on the test to find the angle between two vectors, it's okay to just, you're not going to have a calculator, so you could just write the answer as cosine of theta equals whatever. you would need the arc cosine function on your calculator to like actually obtain the angle from that. But you wouldn't need to do that on a test. So this would be great. Okay, so that's all there is to that problem. Let's move on. I'm gonna put number 10 up here for you. And on number 10, we are working with the vector space of M2 of R. And I wrote down the form of the matrices A and B. And it just says show that the formula that I gave right there for the inner product of A and B, show that this does not define a valid inner product on this vector space. So this is all having to do with the axioms of a vector space. I'm going to write them down again today. You had them in the video that you watched, and then we did write them down on Tuesday. But let's just get them in front of us again today. The axioms of an inner product. The first one was that the inner product of a vector with itself has to be always greater than or equal to 0. And it equals 0 only if we're talking about x equals the 0 vector in the first place. So that's the first axiom of an inner product. Okay?
Number 10,
I'm sorry?
is this number 10?
This is just a general review, and then I'll do number 10 in a second. Yeah, exactly. So that's the first axiom. The second axiom is the one that says the inner product of x with y is equal to the inner product of y with x. Okay, the third one is the one that allows you to pull out a scalar. So if I have the inner product of c times x with y, I can pull the c completely out in front of the inner product of x with y. And then the fourth axiom is that the inner product of x1 plus x2 with y is equal to the inner product of x1 with y plus the inner product of x2 with y. Yeah. So make sure you know these, because if I ask you, this is a very standard type of a test question. I give you some fake inner product, and then I ask you to show that it doesn't work, right? So something about this formula right here is going to be bad. What I recommend that we do when we see a question like this is we run through our axioms. And if we find one that fails, then we can stop, right? Then we can say, okay, it's not a valid inner product. So, and I like to do them, by the way, in this order. The first one is a lot of times is the one that doesn't work. So it's kind of nice to uncover that right away at the start. So let's try it on this formula right here. So if I was looking at axiom 1, that would mean the thing about the first axiom is that you're putting the same vector into both slots, right? So here it's x with x. So now in this context, I'm using matrices. So I would probably write them as A with A. Okay? And all we have to do, guys, is take the formula in the box. And now we don't have any B's anymore. It's just duplications of the A's. So this first term is A11, A22 plus A12, A21 plus A21, A12 plus A22, A11. That make sense? Yeah, so you're just, everywhere you had B's in this formula, now they become just A's again, because it's the same matrix twice. And the question is, must this always be greater than or equal to 0? That's the question. Is it greater than or equal to 0? Well, one thing you might notice, guys, is that the first term and the last term are actually the same. The first one and the last one are the same. And the other thing is the two in the middle are also the same. You actually just have a double copy of the A11, A22, and you also have a double copy of the A12, A21. So you can kind of simplify it just with the algebra by just doing that. So it just cleans it up a little bit. Does this thing that I wrote down right here, guys, does this always have to be positive? You know, if it was something squared plus something squared plus something squared, I would say, oh yeah, squares, you add up a bunch of squares, it's gonna be positive. This is not what we have. We have just 4 random numbers here, right? There's gonna be a way to make that come out negative. And if it comes out negative, then this axiom fails, right? This is axiom 1 from our list. Okay. So what we should do is give an example that illustrates that this could fail. What if we had a specific matrix in mind? Now, the thing about our example, the thing about the specific matrix here, guys, is that we should make sure that, you know, we would like these terms to come out negative. So the easiest way to make sure that that happens is to choose numbers with opposite signs here and choose 2 more numbers here that are also opposite signs. You'll guarantee this thing to come out negative. So like on the A11 and the A22, which are just the diagonal values, right? I just pick, I don't know, 5 and -2. I'm making up anything, as long as they have opposite signs. And then on the other 2 entries, the A12 and the A21, I'm gonna pick my favorite numbers that are opposite signs again. So maybe 3 and -1, something like that. Okay? If you do that, and then you say, well, okay, what's the inner product of A with itself? According to my formula, it's just 2 times 5 times -2 plus 3 times -1, and that is less than 0. Now we can put a big frown face. It fails, right? The axiom failed. So as soon as the first axiom fails, do I have to look at the other axioms? Not at all, right? As soon as one of the axioms fails, then that means you do not have a valid inner product, and you can kind of call it a day at that point. Okay, so this was not a valid formula. Actually, if you wanted it to be a valid formula, the way you would have to have changed it is the valid formula, and I'm writing this down because I need it for the next problem. The valid formula would have been inner product of A and B to be equal to, let me put this camera on it here, would have been A11 B11 plus A12 B12 plus A21 B21 and then plus A22 B22. So you see the difference of the formulas? This one does work. If I change all of the B's into A's, I do get A11 squared plus A12 squared plus A21 squared plus A22 squared. It's positive. Right. So this formula over on the far left there would have worked, but what they asked us on problem 10, notice how they shuffled up the subscripts a little bit? That's actually what led to the demise of that formula. It didn't work anymore. Okay, so let's just really quick do this last example, number 12, and then I think we'll probably be just about out of time for today. To do this number 12, finding the angle between these 2 matrices, we're going to use this valid inner product. You can't use an invalid one, right? It has to be something that's a valid inner product space. So I'm going to use this formula right here, guys. This is the one I want to use. Find the angle. Okay, so what we know that the cosine of theta is the inner product of A with B divided by the norm of A and the norm of B. All right, and let's calculate the numerator and the denominator really quick, and then we'll be good to go. For the numerator, right? For the numerator here, guys, I'm just taking, A11 times B11 plus A12 times B12, etc. So 3 times 1 plus 2 times 1 plus -2 times -2 plus 4 times 1. Piece of cake, right? So it's actually just like a dot product. It's just that the vectors look like they've been put into a 2 by 2 square, but it's the same kind of concept. So boom, 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 add up the 4 numbers and we'll have the numerator. For the denominators, okay, the denominators, we got to do this thing with the norms. Both of them are square roots, right? This one's a radical, this one's a radical. What goes underneath the radical? It's the inner product of the vector with itself, right? So let's make absolutely sure. We've been talking about this all day today, but it's really important. The norm of a vector is the square root of the inner product of a vector with itself. By the way, guys, that is not this. I'm not doing a squared here. I'm literally using the formula over there to do the calculation. So just be cautious about that, right? So in this case, for this first vector, it's just 3 times 3 plus 2 times 2 plus -2 times -2 plus 4 times 4, right? That's the inner product of A with itself. Because you're just doing A11, A11 plus A12, A12 plus A21, A21 plus A22, A22. It's just going to be that. And the second one is just 1 squared plus 1 squared plus -2 squared plus 1 squared. Literally just that. And these are just numbers now, and it's not hard to come up with an answer. 13 on top. And on the bottom, I think this is the square root of 33 here. And this one is just the square root of 7. This is about as good as you can do without a calculator. So you just write that down and call it the answer. Yeah. Okay. Questions on that? Well, I did most of the problems. I didn't quite get to this one, 36. So take it as a practice problem. Maybe I'll do it in the review section. But it's an extra one you can do. The solutions to the homework are already posted. So you can check those out on your own. Thanks, guys. That's all I've got for today. Thanks for being here and for your attention. I will look forward to seeing you in my office hours or at the review sessions or at the very latest next Tuesday.